In this video we are discussing hardware and software concepts of distributed system. Hardware concept of distributed system. A distributed system consists of multiple independent computers, nodes, connected through a network. Each node has its own processor and memory but communicates with others to share resources. This diagram represents the hardware structure of a distributed system. Multiple independent nodes, node 1, node 4, are connected through a common network. Each node has its own processing capability and communicates by sending data over the network. The client node accesses services by interacting with these distributed nodes as a single system. Basically, the hardware of a distributed system holds large pools of computing resources, like CPU, memory, etc., to serve different kinds of applications running over the network. It is made up of multiple autonomous computers, each with its own CPU, memory, and storage. These computers are interconnected through high-speed communication networks like LAN or WAN. They coordinate via hardware and network interfaces to function as one unified system. The pool of computing resources is categorized into two main types: multiprocessor system, multicomputer system. Multiprocessor system. A multiprocessor system is composed of multiple processors and memories interconnected through an interconnection network for the execution of distributed applications. In this, each processor has its own local memory connected through an interconnection network. Processors communicate by sending data over the network when memory access is needed. This architecture reduces memory contention compared to fully shared memory systems. It supports better scalability and parallel performance. Design. Multiple processors and memories are mounted on the motherboard using advanced VLSI design. Addressing. Physical addresses are shared among multiple processors. Cache. Each processor maintains its own cache memory for faster computation or to store recent data. Bus. Processors use dynamic memory modules, slower than cache, using address, data, and control buses. The multiprocessor system has two specific architectures. 1. Private memory architecture. In this architecture, each processor in the system has its own independent memory modules. These modules generate and provide independent memory addresses for every instruction and data executed by that processor. Advantage: each processor uses its own cache and own memory modules for faster execution of applications. Shared memory architecture. The diagram shows multiple processors are connected through an interconnection network. All processors access a single shared memory module. Data can be easily shared since memory is common to all processors. Communication between processors happens via shared memory instead of messages. Performance may reduce due to memory contention when many processors access memory simultaneously. In this architecture, a set of memory modules is shared among multiple processors interconnected by buses. The common set of memory modules generates shared addresses among multiple processors. Requirement: there is a need to keep updating the shared memory addresses used and released by the processors after execution. Disadvantages of multiprocessor systems. Bus overload. Buses become extra overloaded as they serve multiple processors concurrently, degrading performance. Cache inconsistency. There is often inconsistency in cache as multiple processors use multiple caching and replication mechanisms. Multicomputer system. In multicomputer system, each computer has its own private memory and processors. Computers are connected through a communication network. There is no shared memory between different computers. Data is exchanged using message passing via network interfaces. This architecture offers good scalability and fault tolerance. In a multi-computer system, multiple computers with their independent processors and memories are interconnected by a computer network. Networking technologies. Technologies like Ethernet, FDDI, and ATM are used to provide fast performance. Communication. Messaging among multiple computers is done over communication networks. Resource usage. Each computer uses its own processor with separate cache and memory modules to serve requests from different entities of the distributed applications. Software concepts of distributed system. A distributed system is a collection of independent computers that appears to users as a single coherent system. Software plays a crucial role in hiding complexity, managing communication, ensuring consistency, and handling failures. The following are the concepts. 1. Transparency. Transparency means hiding the distributed nature of the system from users and applications so that it behaves like a single system. Types of transparency. Access transparency. Location transparency. Migration transparency. Replication transparency. Communication. Processes in distributed systems run on different machines and must communicate through software mechanisms. Since there is no shared memory, communication is achieved using message passing, RPC, or middleware. IT enables synchronization, data sharing, and correct execution of distributed applications. Communication models. Message passing, explicit sending and receiving of messages. Remote procedure call, RPC, call a remote function like a local one. Remote method invocation, RMI, object-oriented version of RPC. Sockets, low-level communication. Web services, REST, SOAP, internet-based communication. Naming. Naming allows resources and processes to be uniquely identified and located. It separates a resource's identity from its physical location, allowing resources to move or replicate without affecting users. Types of names. Physical names, IP address, MAC address. Logical names, domain names, URLs. Naming services. DNS, domain name system. Directory services. Purpose, decouples resource identity from location. Synchronization. Distributed systems lack a global clock, making synchronization difficult. Key synchronization issues. Clock synchronization, aligning clocks across machines. Mutual exclusion, preventing simultaneous access to critical sections. Event ordering, determining the order of events. Algorithms. Lamport's logical clocks. Vector clocks. Distributed mutual exclusion algorithms. Fault tolerance. Failures are inevitable in distributed systems. Types of failures. Node failure. Network failure. Process crash. Fault tolerance techniques. Replication. Checkpointing. Rollback recovery. Failure detection. Redundancy. Goal, maintain system availability and reliability. Thank you.